last part of chapter 11 we want to hit on is related to science in general. From the text, science is derived from Latin, meaning to know. I like to define science as a systematic way of understanding nature using hypothesis testing, and we'll get to that. But scientists use inquiry, asking questions that allow them to kind of come up with a hypothesis. Answering that question, ultimately they test those questions using experiments. And then those experiments, they get data that are used to either kind of accept or reject the hypothesis. There's a couple different types of data. There's qualitative and quantitative. Qualitative usually doesn't include numbers. Could take a number of different forms, but quantitative usually grab numbers and so on. Here we have Jane Goodall studying chimpanzees. She has her journal where she is taking like anecdotal data. So that would be a good example of qualitative data. Although I can see it's got some numbers, but right there she's taking photos and taking notes. So hypothesis is going to be our we're going to make observations about the world. We're going to ask questions about the world, and then those could be just completely unstructured. It could be you walking outside and making observations and asking questions. It could be you going to the library and reading about all the volumes and volumes of work, and you're like, I wonder what would happen if. Hypothesis is going to answer that question that you generated from your observations. And then that hypothesis is going to lead to a prediction. All right. So the predictions, a lot of times people get confused with the hypothesis, but the prediction is generated from the hypothesis. I usually like to state them in like if-then statements. But it's generated from the hypothesis. It should be like logically generated, and then the experiment will kind of utilize the hypothesis and really the predictions. The predictions should be specific and kind of guide the experiment. The experiment then is carried out, and then a conclusion is made. Let me just go to so here, the observation, and this is kind of scientific thinking. Hey, my desk lamp doesn't work. Well, why does it not work? That's our observation questions. And hey, we've got two competing hypotheses. One is that the bulb was not, properly screwed in. Second one is that the bulb was burnt out. You could probably have other ones. How about number 3? The desk lamp isn't plugged in. The fuse is blown out. You could go on and on. But these will lead to predictions. If the bulb was improperly screwed in, if we reinstall that bulb, then we expect the desk lamp to work. With hypothesis number 2, where the bulb was burnt out, that's not going to we're not going to have the same prediction as hypothesis number 1. Our prediction hypothesis 2 is that if we put a new light bulb in there, that will make the desk lamp work. Okay. So then you test that hypothesis and prediction, but either by reinstalling the bulb or replacing the bulb, and it either works or it doesn't work. Now, you could, for hypothesis 1, probably a prediction that wouldn't be appropriate would be replacing the bulb for hypothesis 1, because that would fix it for both of them, and it doesn't really tell us what the original problem was. Likewise, like going out and buying a whole new desk lamp doesn't help. It doesn't really. It helps us get a lamp that works, but it doesn't really tell us what the problem was. But anyway, this is just kind of a quick little example about scientific thinking. But I do like you can kind of see how the predictions are generated, and a lot of times people confuse the hypothesis and the prediction. They think it's the same thing, and it's not. The hypothesis is probably more general, and this prediction is a little bit more specific. I'm not going to really say much about deductive reasoning, but I do want to utilize this example of I think there were undergraduate researchers studying mice populations out on the coast. And they noticed that they had, within like one species of mouse, that they had two different kind of coat colorations. So populations of mice, Peromyscus polionotus. Let's take a look. So there's some white sand dunes where they live at. And then they live at kind of like more inland with more vegetation. And actual like soil, and instead of just like straight up sand, white sands, and almost like you see the pictures in a minute, and it almost it reminds me of the Indiana Dunes, where you kind of have this like beach that's kind of whitish or kind of lightish in color, and then as you go further inland, you get more vegetation, more kind of darker soil. All right, so here up, and this is in Florida, you've got this white mouse on a white background. You can kind of see some dune grasses here, but it's very really sandy soil. And then further inland, and you can see on the inset here, like we're going much further inland, which is fine. We have got more vegetation, and the soil's a little bit darker. And you might make the argument that we have two separate populations, same species, but one's like inland and one is on the water. Okay, and here you can see give a better feel for what what kind of the environment is for kind of the white colored mouse, and then for the kind of brownish colored mouse, looks like you got like a random tree or so out there. And then you can see the white mouse isn't like all white. You can kind of see some kind of grayish like tufts of fur, and it's interesting because that almost like matches these little depressions in the sand and the shadow. It's very, very fascinating to me. It's not like a polar bear. You get these big dark eyes. And here we have the inland Peromyscus, which isn't all brown either. If you notice on the belly, and underneath it's mouse chin or whatever. It's very white. Anyway, so. Yeah, these more all in all, these mice kind of match the coloration of their habitat, and there's just kind of observations or thoughts, ideas, whatever, that natural predators are visual hunters. So you're thinking like like hawks, and maybe even some snakes, or you could even have like some mammalian predators depending where you're at. Somebody hypothesized that these color patterns could have evolved as adaptations, or helping them be fit to the environment, and protecting the mice from predators. 2010, a scientist by the name of Hopi Hoekstra and some students tested this hypothesis. Well, how are you going to test this? Well, you're going to use some models of mice, basically, and you're going to kind of manipulate them a little bit, but they had their predictions based on their hypothesis, and that was the idea that the mice. Sorry, let me back it up here. What they're going to do is they're going to take, two spots. They're going to look at the beach and inland, and they're going to take like these models of the mice, and they're making them different colors, right? So you've got like one that matches the natural habitat and one that doesn't. And the idea is that, their hypothesis is that this is, predators are kind of like molding this. And the idea is that, then their prediction is that if you don't match the habitat, you're going to get attacked more than if you do match the habitat. All right. So they're doing a manipulation of kind of the natural world, and that's what really experiments are about. They are about collecting data, but we could just go out and collect a lot of data, but if we don't manipulate something, if we don't change something, it's not really kind of truly an experiment. It's not really testing something. We're just kind of data mining, and I'm okay with data mining. I don't want to sound like I'm a snob, but data mining is in a lot of cases is just making a big observation, and observations are important. But if we want to do an experiment, we have to do a manipulation. Okay, so in this one, the manipulation is changing the color of the mice, and as long as that is that the manipulation, it's also an independent variable. It's something that we're changing, and then what they're measuring recorded signs of predation. So that's the dependent variable. The dependent variable, it responds to the independent variable or the manipulation. All right, so they did that. I'm not really sure of all the how many days they did it and whatever else, but if we look at this, so we have two habitats: the beach habitat and the inland habitat, and you've got these. They're going to put out like equal number. They're going to control this experiment. So they're going to put equal number of light models to dark models. What they're not going to do is they're not going to put like 500 dark models and only 2 light models on the beach habitat, because that would not be controlled. And when you control an experiment, you try to keep the variables the same as possible. So another thing that we control is like when they're doing this, they wouldn't just put all these dark models out on one day, and then later on put all the light models out on another day. They're going to put them all out at the same time, and because then these treatments they're experiencing the same temperature, the same light, same weather, and so on. All right, so those are things that are controlled in that experiment. Now, what becomes confusing is that we have a control group and an experimental group. All right, the control group is the group we don't really expect anything to happen. Okay, we expect that to almost be like the normal situation. All right, so that's a control group, and then contrast that with controlled variables. Anyway, they did this experiment, and they found that on the beach, if you matched the background, you're less likely to be attacked than if you did not match the background. And then, lo and behold, they went inland, and they found out that if you matched the background, you were much less likely to be attacked than if you didn't. All right, and then when they did their experiment, they felt like this kind of supported their hypothesis. They were able to get it published in the Journal of Evolution in 2010. So that meant it was peer reviewed. People kind of thought, they kind of agreed with it. They liked it. But that doesn't mean that they're right 100%. What they meant, well, all it is that they did not disprove their hypothesis. And that's something that people kind of have a hard time getting in science, even scientists. You make your hypothesis and you test it. You don't prove your hypothesis. You just didn't disprove it. And usually, when you get like a study, studies like this happen over and over and over again. After a while, you're kind of like, all right, I believe this. Like, I'm pretty sure that nobody's going to disprove this hypothesis. But there's always a possibility. There's always a possibility. And so people kind of think that science is like an objective sort of field, and there's like, this is subject to interpretation. You may not buy 100% of what they did. You might find problems with their experiment, and that might be enough for you to say, what, I don't really believe their hypothesis. Where I might read it and think, what, I think they did a good enough job. I'm cool with this. I'm gonna kind of buy into it. So there's some mice. Anyway, over time though, what happens is, people might really kind of, buy into hypothesis. Science is almost like a popularity contest in some ways, at least of like scientific hypotheses. And over time, if your hypothesis, you've got like this really big hypothesis and it's not disproven over like a long period of time, people might actually start calling it a theory. And a lot of times we talk about, oh, well, my theory on this is whatever. And then, if it's never really tested, it's not really, at least in science, we would not consider it a theory. It would be considered like an untested hypothesis. In order for something to be a theory in science, it has to be tested rigorously many times. And if it's not disproven after a long, long, long time, it may be considered a law. In biology, we don't have a lot of different laws. But anyway, so theory is going to be broader in scope, and it's going to be supported by a lot of evidence and for a long time. And this is kind of where I'm going to cut it off. Although concept 1.4 is interesting. I think it's important to know that science really benefits from many different points of view, and that's, if we don't have those different points of view, if everybody's kind of agreeing with everything, I don't feel like science really grows, because you don't really have a lot of really almost like creativity to draw from. And as much as we want scientific to be very cooperative, it's not always cooperative, especially when money comes involved and lots of grants are out there that people want to get. And usually the people that you're competing to get money for, the grant money for, are also the people you probably should be cooperating with the most, but they want that money just as much as you. And that's where I'm going to stop on the scientific method. Thanks.